In this video here, we're going to take a look at using a minimum spanning tree method to find an upper bound. Now we can use a minimum spanning tree method to find an upper bound for the practical traveling salesman problem by following these steps. So for step 1 then, what we do here to begin with is we find the minimum spanning tree for the network. And you should be aware then that we can either use Kruskal's algorithm or Prim's algorithm to do this. What this does then is it ensures that each vertex is included. Now for the next step then, step 2 here, what we now do then is we double this minimum connector. So what we're essentially doing here is just tracing our steps, right? And this ensures then that completing the cycle is guaranteed. And now for the third step then, what we now do here is we search for shortcuts. And the best thing to do here is to make use of some of the non-included arcs that enable you to skip a repeat of some of the minimum spanning tree. Now, the key here is that we're seeking a minimum root. So it should seem logical to use the minimum spanning tree as a starting point. Now, the initial upper bound found by doubling each arc on a minimum spanning tree as shown in the diagrams below here. So what I've got with the first diagram here is the MST, the minimum spanning tree. What we then do here is we double each arc. And what this gives us here is the initial upper bound. So this visits each vertex and returns to the starting vertex. And an initial upper bound is found by finding the weight of the minimum spanning tree for the network and then doubling it. So for example, if this MST here had a weight of 50, then the initial upper bound for this network here in this problem would be 100, right? 50 times 2 to give us 100. So to finish with then, let's just take a look here at how we can improve our initial upper bound. So to finish with then, as we just mentioned, right, let's just take a quick look here at how we can actually improve the initial upper bound. Now we can improve our initial upper bound by looking for shortcuts. And for some examples, there may only be a choice of say one shortcut. And for more complicated networks, there may be many shortcuts to choose from. Now, we'll learn about the nearest neighbor algorithm later in this chapter, right, which eliminates the need to search for shortcuts. So you'll see later on in the course, or later on in this chapter anyway, that the nearest neighbor algorithm is really quite useful. And what it does then is it eliminates the need to search for shortcuts. So as we just mentioned here, for large and complicated networks, selecting shortcuts can be really quite, not difficult as such, but can take quite a bit of time. And the nearest neighbor algorithm essentially eliminates that problem, okay? Now, the nearest neighbor algorithm isn't perfect in of itself, but we'll discuss that in that video, okay? Now, in either case, the main goal here is to make the upper bound as low as possible. And what this does then is this reduces the interval in which the optimal solution is contained. So that gives us everything that we need here then for an introduction to using a minimum spanning tree method to find an upper bound. So to finish with then, as always, right, let's just work through a practice question together. So let's just get started then with this practice question here. Now, as we can see then for this question here, we have this table. And this table here shows the least distances for a network. Now, for the first part of this question, that is part A, let's just do that at the top then. It just says then by starting at the vertex A, find an initial upper bound to the traveling salesman problem for this network. So to begin with here, because the network is already in the form of a matrix, it just makes sense then to just apply Prim's algorithm to this matrix here, as opposed to drawing the network out and then applying, for example, Kruskal's, right? That wouldn't be very good. That would just be a waste of time, basically. So in that case then, let's just apply Prim's algorithm to this matrix here. So in that case then, we'll make a point here for the arc selection. So arc selection. Because we're starting at A then, I'll also do this in a different color, by the way. Let's just do it in red then, mix it up a little bit. So above A, I'll put a 1 here, above it like so. What we also need to do here is just delete row A as well. I'll do that using a highlighter. So deleting row A then, like so, we get something like the following. Perfect. So at this point here, oops, once I get my pen, there we go. All we need to do here then is just look down column A here. So don't forget then we always choose the smallest possible value, which in this case here is 10, right? I've got a choice of 10, 14, 21, and 32. Well, clearly 10 is the smallest possible value, right? So we circle 10, we put a 2 above B. We then indicate which arc we selected. So we chose AB here with a weight of 10. So AB with a weight of 10. Then what I also need to do here we can't forget to do this, right? Is just delete then this row here. Okay, so deleting this row here, like so. Perfect. Okay, and again, we just repeat this process, right? Now at this stage here, don't forget then, I can't speak anymore. Don't forget then that we do need to look down both column 1 and column 2 here, or column A and column B, whichever you prefer, not just column B. Okay, so I've got a choice then of 14, 21, and 32, or 27, 9, and 24. So clearly, the smallest possible value here is 9, right? So we circle this like so. We then indicate which arc this is. So this is B to D, so BD. With a weight of 9. We'll then put a 3 above D, like so. And then don't forget here that we do need to delete this row. Okay, so deleting this row here, like so. Perfect. Okay, let's just keep going then. So again, we look down both, sorry, not both, but all 3 columns here. So A, B, and D this time. So I've got a choice of 14, 32, 27, 24, 38, and 15. So clearly then, the smallest here would be 14, right? So we circle 14. This corresponds to C here. So we put a 4 above C. We denote which arc we've just selected. So that is AC here. And the weight of AC then is 14. So we're nearly there now, right? Let's just delete row C here. So deleting row C then, what do we get here? Well, what do I get here? I just delete, right? What am I on about? So just delete the row. There we go. I'm getting carried away with calculations. There we go. Perfect. So, like we said, we're nearly there now, right? Just repeat this process one more time here. So I've got a choice of 4 values here, 32, 24, 20, and 15. Well, clearly, the smallest there is 15, right? So we circle 15. That corresponds to E. So put a 5 above E. We then denote the arc here. So that is D to E with a weight of 15, like so. And then again, to finish with here, don't forget that we do need to delete this row. So I'll use my highlighter again. And there we go. Perfect, right? We've deleted the full table here. And in that case, then what we've now got here is our minimum spanning tree. So therefore then, the weight here of the minimum spanning tree, I'll just abbreviate this to MST here, just save me writing this down in full, is, so what I get here then is 10 plus 9 plus 14 plus 15. So 10 plus 9 plus 14 plus 15. If we add those together, what do we get here? So we would get 48. So we get 48 here then for the weight of the minimum spanning tree. But be careful here, right? We don't just want the weight of the minimum spanning tree. What we actually want here is an initial upper bound. So don't forget then, for an initial upper bound here, all we simply need to do then is just double the weight of the minimum spanning tree. So the initial upper bound here is 2 lots of 48. So 2 times 48. That would just give us 96 there. And there we have it then. So this value here, this 96, right? This is an initial upper bound to the traveling salesman problem for this network by starting at vertex A. Okay, so that gives us the solution to part A. And then to finish with here, we have part B. So it doesn't really matter too much, but I'll just change my pen color anyway. So for part B then, what do we want to do here? So it just says starting from the initial upper bound found in part A, is this value here of 96, right? All we want to do then is use a shortcut to reduce the upper bound to below 70. So to begin with here, you don't have to do this, but I do think it is quite a good step to do. And it is quite helpful in identifying, too many tongue twisters in this video, in identifying a shortcut. Okay, so I've got A, B, D, put C here, and then E at the top. Your minimum spanning tree might look slightly different to mine, but that's absolutely fine. I'll just join up and then I'll add the nodes and the, the labels for the nodes and the weights as I go. So this here was C, this here was A, this here was B, this here was D, and this here was E, right? If I also include the weights, then AC, that was 14. So 14 here. AB was 10. BD was 9. And then finally, DE here has a weight of 15. Perfect. Okay. So for this problem here, to be honest, it's quite straightforward, right? In terms of, selecting a shortcut, because it's quite a simple network. Now, for some exam questions, the network that you have might be quite complicated. And in that case, then selecting a shortcut can be quite difficult or quite, time consuming. And that's obviously a problem. So later on in the course here, or later on in this chapter anyway, you will learn about a separate algorithm known as the nearest neighbor algorithm that essentially eliminates this problem, right, of selecting a shortcut. Okay, but for now, unfortunately, we don't have, that algorithm to hand. So in that case, then what we'll do here is just quickly look at the diagram or our network here. And hopefully it's kind of obvious then that if we choose C to E as a shortcut, then it allows us to eliminate the need to repeat AC, AB, BD, and DE. Okay, so let's make a point here. So we can choose. So what did we say then? C to E, right? So C to E with a weight of 20 as our shortcut. Okay. And imagine you join this up then. Like so. This here would have a weight of 20. So at this point here, we now don't need to double each of these, right? So I don't need to double AC, I don't need to double AB, I don't need to double BD, I also don't need to double ED, right? In this case here, we just add 20 to the weight of the minimum spanning tree, right? And that would give us an improved here initial upper bound. So therefore then to finish with here, the improved upper bound here will be given as, so it was 48 plus the weight then of our shortcut here, which is C to E, right, which had a weight of 20. It's 48 plus 20, which gives us 68, right? And 68 here is below 70. Perfect. Good stuff. Okay. And there we have it then. So that gives us the solution to the one practice question for this video. And that brings the end then of this video here on using a minimum spanning tree method to find an upper bound.